percentage yield is a very important number in real-world chemistry. It's a way of quantifying how good a reaction really is in the real world compared to how good you'd think it would be based on the equation. So this is the definition, and it's important to understand what these terms mean. So actual moles of product is fairly obvious. It's just how much product you get from a given amount of starting material. Theoretical moles of product means how much product you would have expected to get based on the equation. So for example, if you're doing this process, if you have, 10 moles of fluorine reacting, then theoretically the equation says that for every 3 moles of fluorine you just get 1 mole of that. So the theoretical yield is 10 over 3, which is 3.33 moles is the theoretical yield. But in reality, if you do that reaction, you won't just get XeF6, because you can get other products. You can get, for example, other fluorides of xenon like XeF2 and XeF4, so you might get some of those being formed. And if you're forming those, you're going to form less of this. So the actual number of moles will be less than this theoretical number. Another possibility is that some of the fluorine might not react at all, because the reaction might be very slow. And again, that would reduce the amount of that compared to the theoretical yield. And finally, it might be that this is just difficult to purify out from the reaction mixture. And so in the process of purifying it, you might lose some material. And again, that would take down the theoretical yield. And again, that would take down the actual yield relative to that theoretical yield. So it's an important number because it tells you whether the method you're using is any good. If your percentage yield is 5%, it means that most of the raw material you're putting into the reaction is basically being wasted because it's not getting converted into the product you were hoping it would get converted to. And that's potentially a problem because a lot of the raw materials you put into the reaction may be expensive, and at a more fundamental level they may be finite resources. If it's stuff that's dug out of the earth, once it's gone, and so you're wasting finite resources potentially if you have a low percentage yield. And also, if it's not making the product you wanted to make, it must be making something else that you don't want, and so you're going to have to dispose of that unwanted material. And depending on what it is, that may be a difficult thing to do in a safe way, without polluting the environment. So when you're asked why percentage yield matters, those are the sort of two main issues: that you want to avoid wasting finite raw materials, and percentage yield tells you how efficient you're being from that point of view, and you want to avoid building up lots of waste products that you have to dispose of, and that may be a difficult thing to do. So in question 1, our reaction starts with hexane 1-ol. So we've got 1, 2, 3, 4, 5, 6 carbons in a saturated chain. That's the hexane, and 1-ol means we have OH attached to carbon 1. And that's being converted to hex-1-ene, which is this. Again, the chain of 6, 1, 2, 3, 4, 5, 6. But 1-ene means that starting at carbon 1 you have a double bond. So that's produced by eliminating water. So that's the equation you should have. And the type of reaction is an elimination reaction because you're eliminating water. Or you could call it dehydration because it's specifically water that is eliminated there. So it tells us that we have 10 grams of this is what we use to feed into the reaction, and at the end of it we get 7 grams of the alkene. So what we want to know is how good is that compared to what we would have expected based on this equation. And the only way we can answer that question is by turning these masses into moles. You absolutely have to work in moles in all of these percentage yield questions. If you try and do it just based on the masses, you get nonsense numbers. Okay, so as always, as soon as you see mass, you think, right, I need to turn that into moles. So you get moles is equal to mass over mR, which is 10.0 divided by 102 is the mR of that lot. Be careful to count the hydrogens correctly. If you didn't get 102, that will be why, because you didn't count the hydrogens correctly. Remember, 4 bonds for each carbon tells you how many hydrogens are there. And that number is 0.09804 moles. So according to the equation, if you have 0.09804 moles of this, you should get 0.09804 moles of that, plus 0.09804 moles of water. That's what the equation says. But we know that in the real world, other things can happen, as we've talked about, so that we actually expect we might get a bit less than that. So we work out how much we actually got. So again, we work out moles is mass over mR. And this time, of course, the mR is different because it's a different compound. So we get 7.00 over 84 is the mR for that compound, which comes to 0.08333 moles. So that's what we expected. It's a bit less than that because somewhere along the way we've lost some material. So we can then plug those numbers into our percentage yield equation. Percentage yield is actual moles divided by theoretical moles times 100. And the actual moles is that, because that's what we actually got. 7 grams were formed, we've turned that into moles, so that's 0.08333. And theoretical moles is that, because according to the equation, each mole of that should have got converted to a mole of this. So that's what we would have expected based on the equation. Times 100. And if you crunch those numbers, you get 85.0% is the answer. Okay, so somewhere 15% of that ended up either converted into something else, or not reacting, or somehow getting lost along the way. And, you know, that's not bad, but it's not great. You would want, if you were doing this as an industrial process, to do everything you can to push that number up so that you're making more efficient use of this, and so that you've got less junk formed, which you then have to find a way to dispose of. In question 2 we have hexane, which is 1, 2, 3, 4, 5, 6, chain of 6 like that, reacting with chlorine and being converted into 1 chlorohexane. So again, chain of 6 with a chlorine on the end, and that, as you know, is a radical substitution reaction, so it will produce HCl as the other product, and you need UV light to make that happen. So that's your equation, that's the essential condition, and the type of reaction is radical substitution, which you know about from when we studied alkanes earlier in the course. So again, we can calculate the percentage yield from the masses. So we're told we have 15.0 grams of this at the start, and in the end we get 5 grams of 1 chlorohexane. So that's already ringing alarm bells, because that seems like a smaller number than that, and that's suggesting the percentage yield is low, but we don't know that until we work it out properly using moles. Okay, so we can again start with this and get the moles of that. Mass over mR is 15.0 divided by the mR of hexane is 86.0, which gives you 0.1744 moles. again, the equation says that each mole of that should get converted into a mole of that. One of these goes to one of these, so theoretically 0.1744 moles of that will get converted to 0.1744 moles of this. So that's equal to the theoretical yield. Now we can work out the actual yield. So moles, again, is mass over MR, is 5.00. Again, make sure you realise it's different MR because it's a different compound. So 120.5 is the MR of that, and that works out to be 0.04149 moles. Okay, so we can plug those numbers into the expression. So the percentage yield is equal to the actual moles, which is that, so 0.04149, divided by the theoretical moles, which is that, 0.1744 times 100. And if you work that out, it comes out to be 23.8%. So that really is quite bad this time, because that's saying that we get less than a quarter as much of this in the end as we would have expected based just on looking at that equation. And so in part C it asks us to suggest why it should be so low. And this is a point we've talked about a lot in relation to this reaction, that the problem with radical substitution is that you can substitute at different points in the molecule. So we wanted to substitute at carbon 1, but we could have substituted at 2 or 3 and got different products. These, at this end, these are 1, 2 and 3 as well, so 3 different mono-substituted products you could make, but also of course you could potentially substitute more than once. So the answer for part C is really those two things, that the percentage yield is low because the substitution reaction can produce a range of products with chlorine being substituted at different positions in the molecule and potentially being substituted different numbers of times, and so the desired product will only be one of many possible products that could be formed. In question 3 we have this reaction, which is the overall reaction for anaerobic respiration in yeast. So they take glucose and convert it basically into ethanol, which is why it's used in brewing and processes like that, and carbon dioxide is produced as well. So we can approach this in the same kind of way and say, right, calculate the moles of glucose that we started with. So moles is mass over MR, which is 10.0 over 180.0 is the MR of glucose, which comes to 0.05556. And then we can calculate the moles of ethanol actually produced. So again, moles is mass over MR, which is 3.00 over 46.0 for ethanol, which comes to 0.065217. So that's our actual yield of ethanol. So part B asks us what's the theoretical yield, and in the previous two questions that was the same as the moles of starting material. But the point is this time that it's not the same, because the equation says that 1 mole of this should produce 2 moles of that. So however many moles of glucose we start with, theoretically we should get twice that number of moles of ethanol. So the answer to part B is that the theoretical yield, and I'll just put based on the equation just to remind you that this is where the factor of 2 comes from, is 2 times the moles of glucose used, which is 2 times 0.05556, which is 0.1111 moles. So that's theoretically what we should get based on the equation. So then we can do the percentage yield in the same way as usual. Percentage yield is actual moles over theoretical moles times 100. Which is 0.065217 divided by 0.1111 times 100, which works out as 58.7%. So again, we might ask, it doesn't ask you to speculate on this in the question, but it's just interesting to think, why is that number low? It's not, tremendously efficient process. And again, there are various possible reasons. One is that there could be other products. For example, if there's some air around, some of that glucose might react by aerobic respiration, which turns the carbon into carbon dioxide instead of ethanol. So that would certainly be a possibility. And another one would be that one of the problems with fermentation is that this material is actually toxic to the yeast, and so once you've produced a certain amount of it, the yeast die because they basically have poisoned themselves with their own waste product there. And so it could be that some of the glucose remains unreacted because the yeast died from alcohol poisoning before they could convert it. So again, that would be a possible reason for the yield being relatively not spectacular. Question 4, we're oxidizing propan-1-ol to propanal. So propan-1-ol is that, and when we write an oxidation equation, remember we use magic oxygen like that to represent the oxidizing agent, and that produces propanal, which is this. Okay, so we've turned the primary alcohol group into an aldehyde group, and that forms water as the other product. Okay, so that's your equation, which it asks for first, and it asks for a method. So that requires aqueous acidic potassium dichromate is the reagent, the oxidizing agent. And remember, with primary alcohols, the issue is that there are 2 possible oxidation products. You can either make the aldehyde, which is what we want, or if you oxidize further, you can produce the carboxylic acid. And the way you make sure you stop at this point is that you heat under distillation is the key method. And that would be all you needed to say to answer the question. But if you asked to explain that, the idea is that it removes the aldehyde from the reaction mixture. So it can't be further oxidized. So distillation is an important method when you're trying to stop at that first stage of oxidation. Okay, so then we come to the calculation, and this time it's a bit different, because this time it tells us what the percentage yield is in a given setup for doing this, 88.0%, and it tells us what mass of starting material we've got, and asks us basically how much product are we going to get, what mass of product are we going to get at the end. So if we take our definition, okay, so percentage yield is actual moles over theoretical moles times 100. Then this time we know that, because we've been told that's 88%. We know what the theoretical moles can be, or at least we can easily work that out, because theoretically this equation says each mole of that should be converted into a mole of that. So if we work out the moles of this, that will be the same as the theoretical yield, so we know that number, and we've got to find the actual moles. So we can just rearrange this equation and basically get, if we switch that around, so theoretical moles, we're going to slide that diagonally up, as you do when you're rearranging these things, so it's going to slide diagonally up onto that side. So we get percentage yield times theoretical moles will equal actual moles times 100. So then if we slide the 100 over there, diagonally again, so we divide by 100, that will give you the actual moles. So we can just find the numbers then to plug into that. So we know the percentage yield, but we've got to work out the theoretical moles. So we've got to come over here and say, right, moles is equal to mass over MR, which is equal to 250 over 60, which is 4.167 moles. Okay, so that's what we're starting with in the form of our 250 grams there. And theoretically, the equation says if we start with 4.16 moles of this, we should get 4.16 moles of that, because 1 goes to 1. So we can say that that's equal to 88.0 is the percentage yield times 4.167 divided by 100, 3.667 moles, and we can then turn that into mass. So mass is equal to moles times MR, which is 3.667 times the MR of the product is 58.0, which works out as 213 grams is your answer. Okay, so just be ready to rearrange the definition in the same way you would rearrange any other algebraic expression to solve for the one that you don't know, which in this case was the actual moles.